System level, what we do is we start with the system, how it works, what it does, what the components do, not how they do it, what they do, right? You understand? And then we move to the components later. So some of y'all haven't had the sensor class. So originally, when we set the course up, we wanted everybody to have sensors. And what do we do in the sensor class? We don't only teach what they do, we teach how they do it, right? You understand that? Well, what we're dealing with now in our troubleshooting is that we call this. So to trouble, what is automation? Right now?
Automation.
Everybody knows what automation is. So we call this automated manufacturing. So what does automated mean? With little or no human intervention. So full automation means that we do it without anybody there. We just turn it on, and after that we just let it go, right? We don't have total automation anymore, especially anytime you got mechanical and electrical devices. They're going to do what? They're going to break. So I don't think, well, if we ever get to the point where machines are fixing the machines, then which may occur, guys, but it's not going to occur in your lifetime. So what we're doing now, and so what the maintenance person is required to do now, first of all, it's becoming it's the norm now for maintenance people to be versed in multiple crafts, multiple trades. In the old days when we were at US Steel, we had electronic repairmen, we had mechanics, we had what they call riggers, we had welders, we had all different types of things. Electrical would be electronic or electrical, anything that operates off electricity. Well, they are, because they're separated. It's like here at the college, we have an electrical program and we have an electronic program, even though they intermean to each other. Electronics deals with a certain aspect of something that operates off electrical, which means it operates off of what we call solid state devices, which are electronic devices. Electronics devices they're all electrical devices, right? But they consist of the internal components that make the device work. So this computer operates off electricity. So I need to understand electricity, but it's an electronic device, right? So I could be an electrician and I could fix the electrical, but I have no idea how to tear this thing apart and do anything inside of it. I would have to have more of an electronic background, right? So electrical basically deals with the power, distribution of power, and the electronics would actually be the components that operate within it. Okay, that makes sense. Mechanical. So we're going to deal with a little bit of electrical. We're going to deal with some electronics, but not from learning components. We'll have to learn just a little bit when we get into our solid state or electronic sensors. And what does the sensor do? Somebody else should know that. Could be analog, could be digital, but it's going to take some type of physical quantity, right? And it's going to convert it over to electrical, right? You understand? So your sensors you have in your hands. So we say we have 5 senses, but we got a lot more senses than that, guys. But we have these nerves, right? And what does nerves do? Well, they take physical quantities and convert them over to what? Electrical quantities, which is what our computer processes. So that's basically what a sensor does. It does exactly what our senses do. So we got electrical, electronic. This is where we're going to get into our sensors. We'll look a little bit at like motor controls, but we're not going to be concerned with what's inside of them. We're going to be concerned with what they do. So that's what a system level approach does. It means you understand the system. right? So you understand what this sensor does in the system. If the sensor don't do what it's supposed to do, you don't care if it's solid state. You don't care how much electronics it's got in there. You're going to replace the sensor, right? You understand? So used to, when I was first got into U.S. Steel, we fixed everything. I mean, there was nothing that left the gate that was electronic. We tore it apart and we repaired it, right? You understand? And that's back when these things would cost $1,000 or so. It's just like, you know, when computers first came out, the IBM personal computer cost over $2,000, and this watch right here will do more than that computer will do, just about it, right? You understand that? So now what's happened with integration, you know, putting multiple circuits, we're making things smaller, and smaller they get, the cost goes down. So now, you know, instead of me fixing this computer, if it goes bad, what am I going to do? I'm going to replace it, right? You understand? And that's what we did. So your phone, you crack your phone all up, your glass all up on your phone. You know, you could go and get it repaired. But most people say, well, I wanted a what? I wanted a new phone anyway, right? TVs. Used to, there was TV. We had like 4 TV repair places right here in Bessemer. Because you were paying hundreds of dollars for your TV. You're still doing that, but basically now, by the time your TV goes out, because they're so rugged now, you say, well, I wanted a higher definition TV anyway, right? So now we have TVs that look like dang. You know? Huh? Yeah, they got the ones that got the curve in it, and then they. Because they got the flexible LEDs, the flexible circuit boards now for the LCDs, which is really neat. So we're going to look a little bit at electrical from what they do and not how they do it, right? You understand? We're going to look at mechanics, fluid power, and we'll play around with PLC just a little bit, but not from the programming point of view, from the outside point of view, how we connect to them, how do the sensors connect to them, how can I tell if the PLC is seeing a sensor as good or bad? How can we use the PLC to help us troubleshoot what's going on, right? Because your ultimate goal now is not to go out there, especially in electronics. Yeah, electronics, we don't hardly repair anything because it's just too costly. So Amazon's coming on board right now. They're paying $15 an hour for anybody, so I don't know what they're going to pay to their maintenance people, but it's going to be a lot more than that, right? So they're paying you $20, $25 an hour. They're paying for all this other type of stuff. You got a sensor out there that costs, you know, $50 to replace. You think they want you to fix that? No, because by the time you got it fixed, you've already cost them $500, right? You understand? For something they could have got what? For $50. So most of our stuff troubleshooting now, very little electronic troubleshooting. We do have electrical troubleshooting because we still have problems going on there, right? That would cost a lot of money. Electronics is usually replace stuff. Mechanics, this is where we start getting into things that could go wrong where we might have to get our hands dirty, right? And then the fluid power, piping and stuff like that, we'll look at that. But PLCs, or programmable logic controllers, we're going to look at, in this class, we're going to look at it from how we connect it up, right? And how it will help us troubleshoot to get the line back up and running as fast as we possibly can. So electrical, everybody in here has had DC, right? If everybody had AC. Some of y'all have. Well, we looked a little bit at AC. AC and DC are not the same, right? You understand it? Just the little thing that I showed y'all. Takes a lot more AC voltage to get the effective voltage than what we thought, right? So here's our different type of components. We have DC power sources, right? So in DC, we have voltage. Everybody okay with voltage? What did I leave off at? Well, it's in its name. Current, resistance, and then power. Of the three, which is probably most important? But we couldn't do anything without current either. We wouldn't have current without voltage. Power is work, guys. Power is how much work you get out of that voltage and that current and that resistance, right? So power, so like your power, Alabama Power generates voltage and they generate current, and they work into resistance and inductive and reactance, but you don't pay a current bill every month. You don't pay a resistance bill every month. You don't pay a voltage bill every month. You pay a power bill. Why? Because that's how much work you get out of what they provide. So we can't have current without voltage, right? Can we have voltage without a current? Yeah, because we could push into a infinite resistance, but still that. AC voltage, we got, not only do we got resistance, we got something called reactance, which we don't have in DC. So anybody that tells you that AC and DC are the same, they're not. So we have an opposition in AC called reactance. Because what we have in AC that we don't have in DC is we have some terms we need to look at, and it might be in this slide. If it's not, we'll go ahead and talk about it here. So AC, when we generate AC, and we're looking at AC that's generated, it's generated in these guys right here. It don't have a little up there. This is these guys are supposed to be mirror images of each other, guys, but this is hard to draw. And then 0 would occur somewhere down here. Well, these guys keep repeating. They keep repeating, and every one of them are exactly the same, right? So what we do is we divide this down in terms. So one repetition of this repetitive waveform. Anybody had AC? What do we call this? We call this a cycle. So Alabama Power is generating cycles. How long do they generate it? 24/7, right? Cycles. Cycles. Well, these cycles are occurring at a certain rate. So we call them cycles per second. So what's the cycle rate for Alabama Power? Yeah, 60 cycles per second. Now, what happens in electronics, any type of physics or something like that, people that are fundamental in the development of the technology has the honor of having things named after them. So we have a guy called Hertz, and we abbreviate it uppercase H, lowercase z, so they'll say 60 hertz. What does 60 hertz stand for? Cycles per second. It's supposed to be abbreviated with an uppercase H and a lowercase z. So Alabama Power generates 60 hertz, 60 cycles per second. And we get an effective voltage, right? So we get a lot more peak voltage. You understand what I mean by peak? That would be measured from the top of the positive and the bottom of the negative. It requires a lot of peak-to-peak voltage to get a certain amount of work out of it. So then we got DC. So this is AC. Then we got DC. Now, why do we have two different powers? Why don't we have two different ways of transmitting power or getting power? So what advantage does AC have over DC? And what advantage does DC have over AC? DC can be stored in batteries and stuff like that, but that's not the advantage. But that's a good one. DC we can store it and use later. Huh? DC we can electronically control DC. So every electronic device you've got operates off DC, even though you don't look like they do. So what we have is we have these devices called power supplies. These are DC power supplies. And what does this guy do for us? Takes AC and converts it into DC because this is an electronic device, right? Understand? So your car, we call them alternators. So they generate AC. But right off the bat, they're going to turn it into what? DC, because everything in your car operates off of DC. Everybody understand that? That's why you can run it off the battery. One of the biggest advantages we get of AC is that we can induce AC into things. So to induce AC into something, we require three things. Anybody know what they are? Magnetic field. If you're taking my classes, about every class I teach, I go through this. Now what happens anytime we pass current through a piece of wire? This is one of the devices that we have. I don't know where my electromagnet is. I need to find it too. So this is I'm creating something called a solenoid. So all I've got here, this is magnetic wire. This is the problem we have in motors, is that we're trying to couple the magnetic field. So anytime I put electrical current through a wire, it creates a magnetic field. And if the magnetic fields are, a current through a coil of wire, and it rotates it around it. I don't forgot the road, but I think it's the left-hand road, where it's different for conventional current and electron flow. One of the roads is you point your finger in the direction of the current flow in DC, and then the fingers would wrap around the way the magnetic field is being generated around the conductor. So AC is what's happening, is this rule is constantly doing what? Swapping back and forth and back and forth and back and forth and back and forth. Everybody okay? So if the magnetic fields are in the same direction, they combine with each other. If they're in the opposite direction, they attract, right? You understand? So if I can force magnets together and hold them in there and keep them from pushing apart, then the magnetic fields would combine. Which means what? It means we can get a lot more magnetism out of that. So this is what we call magnetic wire. So it's got how much we can couple these magnetic fields depends on how close we can get these conductors together. Well, I can't put two pieces of metal conductors together because they would short circuit, right? You understand that? So they coat this magnetic wire with a real thin coating of insulating paint. That's why it's orange right here. And you can burn that off with a cigarette lighter because it's so thin. Well, we wrap them really, really close. And then what I have here, of course, is I have a straw that all this is wrapped around. And I'm going to come up here and hook this up to my power supply, in which I'll show that it generates a magnetic field. So I got a nail I'm going to put in my center. I don't know if I can be able to show this. By the way, I need to turn my camera over to the side. So let's put the camera on the side so we can see it. So y'all see my nail? And then I'm going to come up here and just touch this. You see what happens? Well, that proves that I'm generating a magnetic field just by putting current through wire. Right? You understand? Makes sense? By the way, what I've just done is I've created an electronic device called a solenoid. So a solenoid generates a linear motion. And so when we put power on it, it would pull things up and put it back. Where do y'all run in a solenoid? Anybody got a washing machine? How does it turn the water off and on to the washing machine? Got a solenoid back there. And this plunger stops it up, and then when I put it on cold water, it does what? So it opens a valve for you. So we got solenoids in washing machines. We got solenoids in, cars. It depends. The problem with a solenoid is that it only generates force in one direction. So what to get it to go back to the other spot, we either got to use gravity, right? You understand that, or we got to use a spring. So your car locks can't use a solenoid. Your door locks. Why? Because we wouldn't have enough energy to make it. Once we unlocked it, we couldn't do what? We couldn't lock it. So they use a little electric motors. But other situations, your starter in your car has a solenoid in it. So what happens is when you hit start, it pushes the gear into the main gear on the back of your motor and starts your car until it starts, and then it drops back out, right? You understand? So we have starter solenoids. If you got a lawnmower, riding lawnmower that's got a starter on it, it's got a starter solenoid in there, right? So if I can generate a magnetic field, so just using a bunch of coils of wire, I can generate a what? A magnetic field. Okay, then if I make that magnetic field pass through a conductor, then it's going to generate a voltage into that conductor. So we need a conductor. And then what do we need, number 3? Yeah, we need motion. So what we have to do is that if I take a magnetic field and I have a magnet and I move it through that conductor, then it would induce a voltage. It would take the energy of the magnetic field and induce a voltage into the second conductor without making physical contact with it, right? Or I could take the magnetic field and move the conductor. So I can move the magnet or move the conductor. What you have to do is the magnetic field has the conductor cut through it. So we call it relative motion, which is one of them's got to occur. So notice here when we put voltage on this thing, this is going to create a current through the wire. It's going to create a magnetic field. Okay. And then when it comes down here and changes direction, the magnetic field's going to swap. Right? You understand that? So what happens with AC, we automatically get motion with the magnetic field. So the AC automatically generates motion for us, right? You understand? I don't have to move anything. So what determines the amount? So y'all that said me before, what determines the amount? Well, we're going to say the size. But I know, you know what strength, there you go. Yeah, strength of the magnet. Because I could have a big magnetic field, right? That would be what? Very weak. And then, of course, would be the number of conductor loops. So that's why when you look at transformers, you have all type of conductor loops. I think we got a transformer here. And then the third thing would be the speed of the motion. So what we can do is we can couple electricity through wires. That my transformer. You'll have to look really close here. This is a transformer. So a transformer allows us to couple energy through the air. So when you look at this, you'll see inside this. Now what we have here is we have something that deliberately concentrates the magnetic field between the two windings of the transformer. So basically the transformer are just two windings, right? And what happens is that when this guy here has AC in it, it's going to generate a magnetic field, which is going to cut these and generate an EMF, electromagnetic voltage, right? But we need to couple these two windings together because the better we have, they call it the coefficient of coupling. So we wind the wires, we wind them on top of each other like this most of the time. And then we put a big chunk of metal out here to concentrate the field. Now the problem is that the metal, if this was a solid piece of metal, it would act like a shorted, we call it a shorted, it would act like a conductor itself. So what they do is they break this up into individual little, we call them laminations, but basically they're little thin plates that are covered with insulators. So the current induced in one of them does not add to the current induced in the other. So we call this a lamination. So you can tell anything that uses AC. So if you ever take a motor apart and you look at the concentrator that concentrates the magnetic field, it's going to be laminated like this. And of course, these are the windings. And you can actually see them, and they're actually wound on top of each other. So this is what they call an E-core, because you can actually see where they got it sealed together. But it's wired around the center, and all this does is do what? Concentrate the magnetic field between the two windings. And they're heavy. They got a lot of copper. Transformers cost a lot of money, right? But what I can do now, how much voltage you induce from the primary. So the side of the transformer that points toward the load, we call that the secondary. And the side of the transformer that points toward the power source, we call that the primary. So how much you couple through depends on how many turns you have in the primary and how many turns you have in the secondary. So if I have two turns for every one right here, then if I put 120 volts RMS over here, then I would get 70 volts. I'd get 60 volts RMS over there. So we call it a turns ratio. Now usually it's always to 1. So most time people say it has a ratio of 6, but that would be what? 6 to 1. If I come over here and put less turns in the primary and more turns in the secondary, then if this was a 2 to 1 and I put 120 volts over here, I get 240 volts over there. So what we can do with a transformer is we can step the voltage up or step the voltage down very easily. So what we have to understand is primary, we can't change energy, right? So energy if we had a perfect world, the energy I put into a system would be the energy I get out of a system. But technically, it's energy in is equal to energy out plus times the efficiency. And the efficiency of a system will always be less than 1. Most of your transformers now are like over 95% efficient. So if we consider them to be perfect, that means if I've got a load over here that requires 100 watts, then my primary would have to provide 100 watts. So transformers don't change energy. They can't change power, right? They can't change the amount of work. They just give you that work at a different voltage. So when we say transformers change the amount of voltage, that's not true. They change the amount of voltage, and they also change the amount of current. Because if this is, so if I've got 120 volts over here, and I've got 12 volts over there, and over here I'm getting 1200 watts of power. Let's say 120 watts of power. Then that's going to be 10 amps. Right, you understand that? Okay. Over here it would be 1 amp. Because the transformer don't change power, right? You understand what I'm saying? Does that make sense? When we talk about in Ohm's law, it's relative to the load. It's not relative to the power source. So in Ohm's law, we learned that if V goes up, I goes up. But that's relative to the load, right? In power transmission, we're talking about the source. So the higher I can make that voltage, the less current it's going to require to deliver that power. You understand that? Now your loads are going to be designed around a certain voltage, right? Just about all of them are. So if you look at your TV, it's going to say 120 volts. Well, if you come up and you rewire that because you've only got 240 volts available, and you rewire it, you go out down to Lowe's and buy a plug and put a 240 plug on there, plug it into 240, what's your TV going to do? It's going to blow up, right? So loads are designed to deliver a certain amount of power at a certain voltage. So what advantage does high voltage have? So guys, if I could transmit my power, because what we have to understand is there's no such thing that has no resistance at all. And what's the formula you learned in DC as far as voltage drop goes? How do you calculate voltage drop? What's the formula for voltage? That's voltage drop. Yeah, V is equal to I times R. So Alabama Power is trying to send you power. It's trying to send you power at voltage, but to get power, not only does it have to have voltage, it's got to have what? Current. Every wire has resistance. If I put current through a piece of wire, I will have a voltage drop. What determines how much resistance a conductor has? Huh? We'll go first. First of all would be the material. This is the order. Material. What's it made of? What's it made of? So we got two primary conductors out there. We have copper and we have aluminum. What advantage does copper have over aluminum? It has less resistance, right? So that means it can handle more current with less voltage drop. Yeah, the size of the gauge. Then 3, length. Yeah, this is the order. And then 4 would do the temperature. All metals, if you heat them up, their resistance goes up. And this is what Alabama Power has to take into consideration. So I've got 240 volts I've got 240 volts coming out of in my house, right? 240 volts at one time. Does Alabama Power generate 240 volts? How far, anybody live next to a house? How much power would be required by your neighborhood? Just say a lot. Right? And they're trying to give you that at 240 volts, right? 7,000 watts of power, 240 volts, right? You'd be talking about thousands of amps through a conductor that runs miles, right? You understand? So what do? Well, what they're trying to do is they're trying to sell you power. What's the formula for main power formula? So this is the formula, guys. I is equal to P over V. That's the guy. This is Alabama Power. So if they're trying to give you a certain amount of power, the higher they make that voltage, the less current it's going to require to give you that power. Right? You understand? And the analogy I use, some of the high tension lines are 750,000 volts. 750,000 volts means they could give you 750,000 watts of power with 1 amp of current. Y'all understand that? So, but I cannot get 750,000 volts close to ground, right? You understand? And plus 750,000 volts with 1 amp would still vaporize you, right? You understand that? If it got into it. So what do we start doing? The closer we get to ground, we need to start making it what? We need to make the voltage go down, but if voltage goes down, current's got to go up, and now the conductors are required to get bigger. But if I'm sending it at 750,000 volts, instead of using copper now, I can use what? Aluminum. So just about all your high voltage lines are aluminum, right? The closer I get to ground, these lines out here are probably copper. Even though they look like aluminum, they're probably copper because they got what on them? They got oxidation on them, right? So, or there's some type of, yeah, we found that out. We had a truck, a big old tractor trailer was unloading at the bookstore over in Building A. When they took off, they cut across the parking lot. So instead of going out to the perimeter road, they cut across the parking lot. I don't know if y'all seen the down drop for B building over there, but it comes down from across the road. We have 3 phases across the road. Comes down, and guess what happened? He caught that down drop on the top of his, I don't know how fast he's going. That sucker broke the top out of 7 telephone poles around the perimeter road. And what happened to all those wires? They came in, fell on a bunch of cars. Burned, you could see the copper because it melted, burned up some cars, messed up some cars. Oh yeah, I was live. We lost all the power at the college. We do that every once in a while, and we were out. In Alabama, and it happened on like a Thursday, so we couldn't come on Friday. And they came out here and they had it fixed by Monday. They had all the telephone poles and everything.
Well, what would have happened to a person in the car?
And luckily, well, odds are that'd have been okay because you're inside a metal. You're inside a metal case. If you had touched the car, you'd have been messed up. But it kicked out so much current, it kicked out the break. We got our own substation. I don't know, you can see it when you come in on the right-hand side, when you go past the Millsap Mill. We have our own substation up there for the college. And it's got circuit breakers on it, so it kicked out the breakers. So, Nobody got hurt. Everybody was in class. I don't think anybody was out there. But it made a lot of noise. So everybody came out and looked.
He just drove off.
No, he was tangled up. He couldn't get anywhere. So, I don't know if he lost his job in it, but that company got sued. So I don't know if they had insurance or not. We did. Yeah, the college had to sue them because what was they doing? They was driving a truck where they shouldn't supposed to be driving a truck. So that's the advantage of AC. AC induces current. So we have what we call induction motors, where we literally induce the voltage and the current into a rotor without having any connection to it at all. So AC motors, we have induction AC motors where the rotors don't even have an electrical connection on because they induce the voltage, and that's why they call it induction motors. So AC, the big advantage of AC is a lot more efficient to do what? Transmit. Because we can step the voltage up for transmission, right? And then step it down. What advantage does low voltages have over high voltage? Safer, yeah. So safer. That's exactly the two reasons. What advantage does DC have over AC? Well, DC, we can electronically control DC. And we live in an electronic world, guys. I mean, there's very few things now that don't have electronics in it. Originally, when you got into a car, the only electronic device in the car was a radio. And that was it. And then everything else was just run by relays and stuff like that. Even firing the spark plugs was done by a distributor cap that just spun around. So we live in an electronic world. So we're going to deal with a lot of DC because we can electronically control DC. In fact, we can take DC and re-oscillate it and create AC. Anybody that's got an inverter that they use in their car, that's exactly what you're doing. You're taking a DC system and electronically generating what? Generating AC. So, and like Anthony said, another big advantage of DC is that we can store it. So we can store that AC. So we have these uninterruptible power supplies. Like at Alabama Power, we was up there, and they got a big old room that's just full of batteries. Big old batteries, biggest ones I've ever seen. So if they lose power, they don't even run a generator. They just switch over to a big old inverter, and they run their building off those big batteries. So you can buy uninterruptible power supplies for your computer. I've got one on mine at home. We got one on our server over here. And that's what it does. It takes batteries and does what? Stores the energy in a battery, and when power fails, it switches over to an inverter, so those are uninterruptible power supplies. Anybody got any of those? Uninterruptible power supplies. People call them UPS. Have you ever heard of UPS? That's an uninterruptible power supply. Normally, your servers and stuff like that runs your computers, it will have an uninterruptible power supply. I don't know. And that's what they're rated at. So when you buy an UPS, it's going to be rated at a certain duration that it can run. The less time they run, the cheaper they're going to be. So most of your operating systems you can install an application on your computer which will shut the computer down when the up starts running down. So it's better to go through a shutdown procedure than it is to turn it off, right? So right now, if I was to pop the battery out of the back of this computer, we could cause problems. So what we need to do on computers is you need to take them through an orderly shutdown, just like you do a manufacturing line. If you know you're going to have to do maintenance on them, then what should you do? You shouldn't just go out there and do what? Kill the power. You should take it through an orderly shutdown where you know you won't have any problems to do what? To bring it back online. Good question, Jeff. So DC and AC. So AC is not the same. We have to deal with something called reactance and impedance. We deal with something called true power and apparent power. So what's the problem with AC is AC, it can create phase shifts between your current and your voltage, which really gets weird. So when your voltage is maximum, your current might not be maximum. And that's where, so what happens is we end up with a type of power called apparent power. And this is what you pay for. So we have different ways we can compensate for that. Conductors, are we okay here? Copper. What's the best conductor what's the best known conductor of electrical current? Go. No. No. Silver. Silver is the best electrical conductor of least resistance. How many silver conductors do you see? Huh? Usually what we do is we use silver as a plating. We coat things, especially like relay contacts and switches, because what we're doing with these guys is we're making a circuit by touching two wires together. And what we want them to do is we want to have very little resistance. So that a lot of your switches, the contact point will be made out of silver. What's the second best conductor of electricity? Don't say that. Copper. Copper is very close to silver. We have a bunch of copper out there. What's the third best conductor of electricity? Gold. Gold. We don't want to use gold. Of course, we would probably not use gold. That's why we don't use silver, because silver costs a lot more than copper. Copper's not cheap, but silver costs more, right? You understand that? Gold has what? Copper rust, silver rust. Silver rust, by the way, is the goodest conductor. Gold, we don't know if it rusts. So we use gold as a plating a lot. Anything that's going to expose to moisture or corrosive like the atmosphere, we'll use a lot of gold plating. Not gold conductors, gold plating. So a lot of things you look at looks like they're gold, but they're not. They're plated. I like to use the analogy about these people that make these fake coins, and they'll say coated with, 0.03 milligrams of pure gold. So that means if you hand them a little while, right, it's going to wear off. So we gold plate. So then we have aluminum is the second most widely used conductor, but it's used for high voltage lines, right? You understand? And so it gets that name because we got so much high voltage out there, right? You understand that? Stranded and solid. Do y'all understand stranded conductors and solid conductors? So what advantage what does stranded mean? We use a lot of small gauge wires wrapped together or whatever to create a bigger wire. And then we have solid wires, which means you have one conductor. What advantage does stranded have over solid? Yeah, the big advantage of stranded over solid is very flexible. What advantage does solid have over stranded? It's extremely easy to terminate and to splice together. So terminate every conductor. What's the function of a conductor? What's the function of the conductor? To get the power from the source to the load. So every conductor eventually comes to an end. The process of bringing a conductor to an end, we call that termination. And there's no such thing as a conductor that's an infinite length. and then first conductors break, right? So the act of putting two conductors together, we refer to that as splicing. What's nice about a solid strand wire, if you can splice it just by twisting them together. And then in electricians, they'll put we call them wire nuts, the caps that they put on, that's their insulator. Very easy to splice. And how do they terminate solid strings? We just usually wrap them around a screw or something like that. Stranded wires, you don't wrap stranded wires right together to splice them. You have to use mechanical or crimp splices. You have to splice them with special devices. So stranded wires, you just can't do what? You can't twist them together because they're very flexible, and as soon as you pull it on them, they do what? They spread apart. Solid wires, you wrap them together, you put an insulator on it, either tape them up or you put that wire nut on there, and if you do it right and you screw them down right, you can't pull those things apart. Stranded solid wires, if we want to terminate them, we can just wrap them around a screw and screw the screw down. They're not going to do anything. Stranded wires, you tie them down, they're going to do what we call a bird cage, which means the strands are going to spread out. As soon as you get one strand out from under the screw, then you change the size of the wire, so you change the ampacity rating of the wire. So normally stranded wires, we have to put a crimp lug on or something on there to terminate them so they don't do what? So they don't spread out. So the advantage of solid wires is they're easier to terminate and easier to splice. Less expensive. The advantage of stranded wires is they're what? More flexible. So they're easy to route. Anybody ever run any house wire in Romax? It's rough. Even 14 gauge is rough because why? It's solid wire, solid copper wire, right? Understand? Man, you're trying to run that through a wall and pull it off a reel and get the kinks out of it. It's not easy. And then you move up to 12 gauge, which is for a 20 amp service. So 14 gauges are 15 amps and below in residential wiring. 20 amps is for 20 amps and below. And then we have bigger ones, you're running to some 10 gauge and 8 gauge, you're running your some of your big units, like your air conditioning system and stuff like that. They usually run those under the floor, right, or through the ceiling because they're too big to do what? To run through a 2x4 and maintain the integrity. Control devices. Switches, push button contacts, and sensors. Fiber optics. Fiber optics is a conductor, but it's not an electrical conductor.
I think of those weird lights, fiber optics.
Yeah, the plastic fiber.
You know what I mean?
Yeah, that the tips glow. Really neat.
The lights that glow.
Yeah, what they finally realized is that when we take a light through something where the light runs at different speeds, it causes the light to beam. We call it refraction, right? You understand that? And we see that all the time in water. So you're standing there looking at something and people looks like their legs are real short or looks like their top is bending over and stuff like that. But once we hit what we call a critical angle, but then I could be looking at water from way off and I come up here and look at it. When the light flashes it literally just bounces off. And this is why if you're back from the water and you look at it, it looks like a mirror. They got some pictures out in Colorado where the mountains looks like they're going up and going down because of what we call reflection, right? You understand? Well, what they realized is we could take glass and put it in a tube, and then we could put it inside another media we call cladding. And each one of those would have different coefficients of, we call it reflection. And as long as we didn't exceed what we call that critical angle, then 100% of the light would bounce and travel through the core of the fiber. Now, what's nice about glass? What advantages light out over current, electrical current? Huh? Yeah, sending information by light, then yeah, it has the ability to be a lot quicker, right? We can modulate and send the information a lot faster, right? Another thing that we don't have to worry about is we don't have to worry about So I've got all these power lines coming over here, and I've got AC, 60 cycle AC all over the place. We've got conductors that are unshielded. They're generating magnetic fields. Those magnetic fields are cutting other conductors, which means they're trying to induce voltage into other conductors that are in close contact. We call that EMI, electromagnetic interference. So copper, we got to really trying to send information to copper. We're very concerned with electromagnetic interference, inducing voltages into that would interfere with my data. Plus, when I send information that's changing through a piece of copper, and I've got two wires together, these wires are going to try to introduce an EMF into the one right beside them. So that's why copper is very limited as far as sending high lots of amounts of information. Fiber, there's no such thing as electromagnetic interference. Atomic bomb could go off by fiber and it won't hurt it, right? It might blow it up. Lightning can strike by a piece of copper and it might blow up. We had the guys, when we were originally networking the college, we have firewalls all the way in building A. They couldn't punch through the firewall legally. That's before they did it. So they ran our network cable up through an air vent on the college and ran it across the roof and ran it down into the other. Just copper wire running across the top of the college. They had a lightning strike that blew up the interface card in one whole computer lab because it was copper. We have copper running through the ground from a building, not through conduit anything. It just has a ground rated thing. And lightning strikes the ground all the time, doesn't affect it at all because it's fiber, right? You understand? So fiber is immune to lightning strikes. Fiber is immune to any EMI. So that's another big thing. So we might not send extremely high speeds over there. We just use the advantage of what? So if I've got 100 megabit wired network, then my fiber is going to be only transmitting 100 megabits, right? You understand that? Because it would be a waste of time to do it in that way. So yeah, we're on 100, so 100 megabits between there and there, but we don't have to worry about what? We don't have to worry about lightning strikes or any type of voltage surges or anything like that.
Fiber and the information, it can't really work.
But it can't do power.
Right.
Yeah, it can't transmit power over fiber. Cannot transmit power over fiber. So the big lines that run under the ocean, they have to send power lines out through there to transmit to run the amplifiers. So that's why them suckers are wide, so big. But no, they can't transmit power. We don't have V, we don't have I, so we don't have what. But we can send what? We can send information. We can send information at a high rate of speed. Then we got to have something on this side, some type of sensor that picks it up and converts it into electricity. So this is fiber right here, right? I'm using my air. So I'm transmitting light right here, right? You understand? So there's a guy up in that camera that's looking for flashing light that determines, makes decisions on what to do. Now, I know these guys flash his light, right? Huh? Yeah. You want to take a break? We need to talk about that, guys. We got to talk about that when y'all get back. It probably won't do any good today, but we'll talk about the way we want to do breaks. Y'all, huh? No, y'all do it fine. What we did on a class this class goes to what time? 1:30. So what we did the last time we taught it is we took 1 5-minute break before, we took 1 5-minute break after, and then we let y'all have a 30-minute lunch. So that's your call. Which means we go a long time without breaks. But that's y'all's call. We could have a 10-minute break every hour, or we could do it that way. So we'll vote on that when y'all get back.
Hey, Mr. Reed, this IoT 2A
communication cables. So yeah. We were showing this. Christine's got that neat little thing back there. I don't know if she showed y'all that. But so that's fiber right there. And she was wondering why she couldn't see the light going up through. Okay. Well, that's right. It's not coming out. It's not coming out. It's bouncing down the center of that conductor. So she's only able to see it at the tips. Yeah, usually if you go like to the circus or something, they also. This is an example of glass fiber. This is what we call. This is a type of cable we call multi-mode cable. We're not going to explain that. We have two types. Extremely high frequency uses what we call single mode cable. Multi-mode cable means, basically what it means is the core on the single mode cable is so thin it only lets one light frequency pass through. But it has almost no space between the refraction when it's moving down the core, which means we can put extremely high speeds through single mode cable. Usually single mode cable will have a yellow outside jacket. This is a multi-mode cable. By the way, these are not insulators. All this stuff in here is just in here to protect this glass. So we have, on the standard cable, we have 4 layers of protection. We have the outside buffer. Some people call it a loose tube because it don't actually contact the fiber. Then we have an Armistead coating, which people call Kevlar, but Kevlar is a registered trademark. But if you call it Kevlar, that's okay, guys. But this might not be made by Kevlar. It might be using the same technique. Then we have a inside buffer right here. This is called a tight buffer because this is in contact with the actual outside of the fiber. Then we have what we call a buffer coating, which is the last line of defense. So, I don't know if y'all can see it or not. Yeah, but this outside right here, it's actually outside of the cable, and it's there to keep that glass from breaking. So right now, when you strip all that, you've lost all the protection. So if I was to bend this, it would break. As soon as I strip off what we call the buffer coating, and then this right here is the actual fiber. And you can't see it. Well, yes, we can splice it. So that's what we learn how to do. We learn how to splice. So sure, it's a conductor. The metal conductors break. Sure, but we need to learn how to splice them, right? You understand? So one of the things we teach in cable splicing and installation is how to not only splice, we call it splicing, but it also should be cable splicing termination and installation. So, because this guy here, like I said, this is what I was showing her. If I come up here and bend this too much, I'm going to exceed what we call the critical angle, and that would be me. I like looking at a lake, and I walk up and start looking down at it. So as long as I'm out past here and I'm below the critical angle, then that water surface looks like a mirror, right? You understand? But as soon as I start getting close at it, and my angle gets like this, and light passes through it, and I can see it. So all fiber has what they call a bend radius, which means a bend radius would mean I come out here and put a point out here, and this would be how steep we can bend that thing before we exceed what we call the critical angle. As soon as you exceed the critical angle, then the loss of the fiber shoots up way a lot, right? You understand? As long as you're below that, then you get whatever loss that they recommend for the cable. And then you can't separate what we call the cladding. So the cladding and the core, you can't separate it because they're bonded together. You can't separate. So there's actually there's 4 layers of protection, right? 1, 2, 3, and then the cladding. The buffer coating, or some people call it the clear coating. And then we come over here, and then we have the cladding. So the buffer coating is actually in contact with the cladding, and then the core is inside. You can't see it. You can't separate the core, which is where the light is traveling down. So we have what we call multi-mode cable. A mode in a fiber is the number of paths the light can take to the core. So multi-mode means we have multiple paths that it can pass, which means if we send colored light down through it, then the light would arrive at the receiver at different times depending on the length. They call that modular dispersion. Single mode, you got how many paths? One. So single mode basically usually required. So here we use light emitting diodes on this. This is rated at this multi-mode cable is rated at 830 nanometers, which is basically red. So you'll see these red. So we can see it flash through that, and we've got a tester that we use for a single mode, for multi-mode cable, where we can actually see the light pass through the cable. Your single mode is going to be around 1300, 1350, which is going to put it in the infrared range. Usually multi-mode, since we got to do it so fine and we're trying to send it at one wavelength, usually single mode requires laser at a light you cannot see. And you get people that's looking for the light at the end of the cable on a single mode cable. That's dangerous, because laser's already concentrated light right you under at one frequency. You can literally burn your light. In fact, that's the way they do laser light surgery. That you can't see the light, right? You understand that? So be real careful around single mode, and don't ever look at the end of it. Even if it's multi-mode, running a light you can see, and you don't need to shine that stuff in your light. Point it at something, right? You understand that? So usually single mode, you have to use special equipment to see if it gets through. Multi-mode, you can use. In fact, this is plastic. What's nice about plastic is, of course, it's a lot cheaper, but it has a real big core, which means and it uses what we call stepped index, but it lights bouncing all over here. So that means the limit of ranges that we can use with plastic is very limited. Usually around 100 meters, plastic would be limited to, which would be, it's still around 330 feet, but it's very doable, right? You understand that? So you'll see a lot of plastic used in the industry, as long as they don't have to go too far. And then they might send it through glass until they get close enough, and then they might convert it back over to plastic. That's pretty easy. But they don't have to have that buffer coating on this, because plastic is really durable anyway, right? And what we'll do is we'll pass this around, and what's so neat is see how this thing is rolled up. And what I want you to do is just point this toward the light, and then just look in this end right here and just cover this up. And you'll see light, even off this little bit of light we have in here, it passes through all this without it, very low attenuation. But just like Anthony said, we can't send power through that cable. It's strictly communication. It's just like when we have copper. Copper is either going to be designated for power, or it's going to be designated for communication. Communication, we got to take other things in aspect. We got to start using twisted pair cables. We got to use shielded cables and do other things to compensate for that electromagnetic interference that will get inside copper. That's just a little look in fiber. So, is your company going to use fiber? Well, we don't know. The mines run it all over the place. Just about every sensor they have underground uses fiber, because every piece of equipment they run out of the ground runs off electricity. Very high garbage, all this big machines generating all kind of EMI, and they're trying to run that a long way. So originally, when we have what we call a fusion splicer, where you literally splice the wires, the cables together by melting them together. Really cool. We didn't have one, because the one we bought cost $7,500. We got that. Well, what we did when we taught the course, we had one of our graduates that worked down in Pinco Mines, and he would bring his fusion splicer up so we could teach that. So, those things are very expensive. We'll look at mechanical splices. So that's a pretty good class to take if you want to learn anything about fiber. It's called cable splicing and installation. It's one of your classes. I think it's optional in the ILT. It's an elective. It's not even in the AUT, I don't think. So, programmable controllers. What is a programmable controller? Programmable logic controller is actually the technical name. A lot of people call them programmable controllers, but they're PLCs. So what is it? What's a PLC? It's a computer that's designed to run machines. That is its function in life, is to run machines. It's not in here to play games on, right? It don't support games. It's there to run machines, right? And it programs in a language A lot of people don't understand. Computers have no idea what English is. It has no idea what anything is. All it understands is binary, ones and zeros. We represent it with voltage levels. We either have a voltage that represents what we call a 1, and we have a 0. Zero volts represents a binary 0. And each digit we call a bit, and we can move thousands of bits around. And that's all a computer, inside of a computer, understands. I don't understand that. There was a series on one of the Star Treks where they had a race they called binoids. And they talked in binary, so they did clicks. Nobody could do what? Understand them. And they understand the computer. They was the computer people on the Enterprise. They'd come in and they would take care of things. I think that was on the Generations were there. So what we have to do when we program computers is we write programs in what we call a high-level language, which is basically languages that we understand. And then we run them through a special program called a compiler that compiles it over to the language that your PLC understands. So we run a special application. So we're teaching a coding class now where you can learn how to write applications for Android and Apple phone. Well, the problem is that the applications themselves are the same. It's what compiler you run them through, right? So Android phone speaks a different binary language than Apple phones do. But I can write the programs in a high-level language, and I can run it through a compiler for an Android phone, and it would create the binary language for the Android. Or I can take that same program and run it through a compiler for the Apple phones. This is why just about every program that I have for my iPhone, you can get it for what? Yeah, an Android phone. Because they just run it through a different what? Compiler. So usually what's nice about high-level languages is they're not tied to a certain process. You just have to have the what? The right compiler. So PLCs use programming languages that people understand. The main language they use is what we call ladder language, which is what electricians learn. They learn a language called ladder language. And then we program it in ladder, draw it, and then we compile it over or download it into the PLC. So PLCs, these are what? What do? They run machines. They're programmable devices that run machines. They're specifically designed for that. Then, of course, every circuit has to have a what? A load. So the loads we'll run into, of course, is resistive load, capacitive loads, and inductive loads. We need to learn a little bit about that. We have indicators. We have indicators all over the place. We're a visual species, right? We like to see things. Motors, solenoids, relays, all this other kind of stuff we'll look at. Are we okay? Any questions? So everybody okay with Ohm's law? What's Ohm's law? If you were to describe Ohm's law, what does it show us? What does it tell us? The relationship between what? The voltage, the current, and the opposition in a circuit. Every circuit's got to have opposition, right? Understand? We don't get work without opposition, right? We got to generate we got to generate a force. We got to generate work, right? You understand that? Watt's law. Watt's law is a very important law. What's the importance of Watt's law? Yeah, it's showing you how much work is being done by the voltage, the current, and the opposition. That's exactly right. We pay for work, right? No, ohms is about the relationship between the voltage, the current, and the opposition in a circuit. Not the resistance, the opposition. We have several types of oppositions. In DC, you learned about resistance. Well, what we do is we have two other we have what we call capacitance. We have inductance and capacitance, which is another type of resistance that we run into in AC. Both of them are given. The opposition is given in ohms. So I gave a test on my solid state class last night, and one of the things is talking about the opposition of a Zener diode, and it was rated in Z and not R. Well, anytime you see it's rated in Z, that's something called impedance. And that's not resistance. Resistance does not vary with, if you got a 100 ohm resistor, it will have 100 ohms in an AC or a DC circuit. If you have 100 ohms of impedance, it means you would have zero, you wouldn't see it in a DC circuit. Impedance is an AC rating of opposition to an AC circuit. And impedance varies with this thing right here called F. What does F stand for? So we got guys called capacitors. Capacitors, their opposition goes down when frequency goes up. So the higher the frequency, the less opposition they have. Then we got guys called inductors. Their opposition goes up as frequency goes up. So that means the amount of opposition you get out of inductors and capacitors depends on what? Frequency. And what's so dang cool is that these guys are exactly opposite of each other. So if we put them in a circuit together, they will cancel themselves out at a certain frequency. And we call it a resonant frequency. And for years, this is the way we tuned radios. We tuned radios by having a dial on the front, and we set up, we let it pass a frequency through, and we blocked all of the frequencies through. So Ohm's law gives us the opposition between the what? The voltage, the current, and the opposition. Not the resistance, the opposition. So when you get into AC, we'll start changing Ohm's law, and we won't put V is equal to I times R. We'll put V is equal to I times ohms. Right. Kirchhoff's law. We have two. We have the voltage law and the current law. What does the voltage law deal with? In a series circuit, right? Series circuit has always got to add up to the source of it. In AC, you're going to freak people out. Because in AC, we have phase shifts. And you have to compensate for the phase shift. We like to bring DC into that and show, you have 50 volts supplied to a circuit, and you have 200 volts dropped in the circuit. But it deals with a phase shift. In AC, you'll learn how to deal with the phase shift. What is the current law? What does the current law deal with? Parallel circuit, right? So what does it say? The sums of the individual branch currents always have to do what? Add up and equal the total current in the circuit. So what is a series circuit? Yeah. Well, we got a little problem in that we have this technically, and I try to tell the difference between this. So I've got this technically. This is a series circuit, and then of course this right here would be a series circuit. Now, what's the difference between the two? Yeah, so on this one on the left, we say the applied voltage has to be dropped across the resistor proportional to its relationship to the other resistors in the circuit. Well, here all your voltage is going to be dropped across that one resistor, right? We say current is constant or the same throughout a series circuit as long as the values don't change. This gets people in DC in problems because we'll put out there, we'll say, okay, I've got a 1,000 ohm and a 1,000 ohm resistor. What would be the current flow? You'd say this, and you'll put next question. If I change this to 2,000 ohm, I'll leave this the same. What would the current flow be? And they say, well, it's going to be the same because the current is the same in a series circuit. So people's got an indication that the current is the same in every series circuit. So if I calculate 10 amps, it's going to be 10 amps no matter what resistors I put. So what happens is the current is the same as long as a resistor does not, or a load does not change. So I'll refer to this as a basic series circuit. And then I'll call this a series circuit. because this is a basic series circuit, right? Everybody understands. So in motor control, we say we can't have loads in series, but technically we could have a series circuit, right? A basic series circuit. So series circuits, what do we say about a series circuit? For a set of opposition, the current flow would be equal throughout the circuit, right? The voltage drop across the resistor would be relative to the other resistors in the circuit. The biggest resistor drops the what? Most voltage and does the most work. Everybody understand that? Parallel circuits. What do we say about a parallel circuit? Now, parallel circuit we have to have at least two loads, right? Okay, so what do we say about the parallel circuit? Voltage is the same throughout all the loads, right? What else do we say? Yeah, but the total current, the amount of current a load draws is inversely proportional to its opposition, right? You understand that? Which resistor does the most work in a parallel circuit? The smallest, because voltage is constant. So if everybody's seeing 25 volts, right, you understand, then the one that conducts the most current does the most work. And it's true, guys, what you say about a series circuit, you almost say what? The opposite about a parallel circuit. In a series circuit, if I add additional loads, total opposition goes up. A parallel circuit, when I add additional load, total opposition goes down, right? Because we're adding another what? We're adding another current path, right? And people have problems with that. When I taught DC, luckily I don't teach that class anymore. But once they learn series circuits, they want to calculate every circuit the same. Series parallel, we're not going to run into many series parallel circuits, and we're not going to run into them in electrical controls. We're not going to run into any of them in PLCs, right? Basically, the only time you'll run into series parallel circuits is in electronics. All your electronic circuits are going to be series parallel. And then everybody okay with the color code? What do we use the color code for? Use them all over the place. I can bring a diode over here where they use the color code. It's a 914. That's what the diode is, but it's so small they can't write the numbers on there. So they use the what? They use the color code. Capacitors, they use the color code. Inductors, they use the color code. So the smaller a device is, they're going to start identifying it with the color code instead of a number. The bigger they are, the odds are they're going to move to writing it on the side. So color codes, you're going to run into the color codes used all throughout the industry, right? Y'all need to learn the color code. So here's electronic devices. So let's talk about, let's take a pause right here. So, well, it's pretty straightforward. Let's say diodes do.
Only allow current flow on the primary.
So I've got to get AC into DC, right? So diodes are one of the primary methods we use to do that. We use them for a lot of things, but their primary use is to convert AC into DC. This is one of their uses. They don't give us real pretty DC. There's a lot that goes on to that. But we add other components. We add filters and regulators and stuff like that to get really nice DC. But we start off with diodes. So you got diodes in your car. They call them rectifiers. So that's what the term means. So it's usually outside of your alternator or it's inside your alternator. It depends on how your car works. So we call them alternators because they put out AC, but our car does not run off AC. It runs off of DC. So one of the first things we got to do is what? Rectify it. And how do you think they do that? They got a bank of diodes in there that converts it over to DC for you. We have what we call transistors. We have two categories of transistors. We have FETs and BJTs. These are our current valves. So what water valve? What do we do with water valves? We control the flow of water. We can run into water valves that act like switches where we just turn the water on or turn the water off, right? Like on your washing machine and on your ice maker. A lot of water fountains do that. You press a button, you get full flow, you let it go, it stops. Or we can operate them in what we call the linear region or the active region, where these guys act like where you got the knobs on your sink at house on your house. What can you do with that? You can turn them wide open or you can turn them off, but you can control the flow precisely between one all the way off and all the way on. And that's what transistors do. Transistors are current valves. We can operate them as off-on switches, which is what we do inside this computer right here. All it does is either stores ones and zeros. We turn things on, we turn things off. Most people call that digital. So if they say we got a digital sensor, guys, it means it's either what? It's either on or off. It does it with solid state devices, but it's either on or off. And then we have analog sensors. These guys are going to do devices that give us an analog device, which means it can constantly vary over a wide range. We got a couple of analog sensors on both of our manufacturing. We have what we call NPN PNPs. This is going to come in important. We'll start talking about safety and sourcing as far as sensors go, PLCs goes. But what a bipolar transistor does is it uses a very small current to control a real large current. A FET uses a voltage to control the current. FETs can usually switch a lot faster, but they can't handle the amount of power a bipolar transistor. So FETs, especially MOSFETs, these guys, these guys can really switch at a high speed, but they can't handle a lot of power. This is where your bipolar transistors still come into play. In fact, they've combined it. It looks like a single transistor, but they call it an insulated K bipolar junction transistor. What they've done is they've combined an FET and a BJT in one unit. It's really cool. And that's this guy right here. Insulated K BJT combined the MOSFET, enhancement of MOSFET, fast switching speed, high voltage current capability of the BJT. You're going to run in a lot of these in what we call pulse width modulation circuits, and also variable frequency AC drives. So how do we control the speed of a DC motor? Huh? It all deals with current, but basically we don't have current without voltage. So basically we say they're voltage controlled, because the more voltage we put on the motor, the faster it runs, and the less voltage we put on the motor, the slower it runs. Primarily we control the speed of an AC motor by frequency. So the higher frequency we put on the motor, the faster it runs. The lower frequency we put it on, the slower it runs. So we have but there's more to it than that, but that's just very, very general. So DC motors, we can just vary the voltage we apply to the motor, and it will cause it to run at a different speed. AC motors, we can change the frequency. So electronic drives that we use to control the AC motors, we call them variable frequency drives. And DC motors are either going to be SCR drives, which DC motors are still out there. They're used more efficiently. Well, what we can do with a DC motor, we can make it average the voltage out. Was this in the last class that I showed you this? So what we can do with a DC motor is we can put a solid voltage across it, and it would run at a fixed speed, right? Depending on what. Literally a DC motor, you can run it till it swings itself apart. But what we can do, instead of putting a single voltage on here, we can come over and pulse it with a waveform that looks like this. And what the DC motor will do, it'll average this out and run at a speed of the average of that, which is really, really cool. And what we can do is we can come over here, is I can have the same frequency, and then I can come over here and do something like this. And now the motor would average it out and it would run at a slower speed. We refer to this as pulse width modulation. And this is the way it's done now, guys. No, it's DC. AC, we have to control it with the frequency and the voltage too. We'll have to look at that. But what we can do with a DC motor, we can control its speed precisely by putting pulses into it. And what we do is we vary the width of the pulse width, the positive pulse width. And it'll average that speed out, and we can control this. Well, what's nice is this is digital. Computers love what? Digital. So we can buy PLCs now that supports pulse width modulation out of the PLC. You don't have to have an electronic circuit. The dang PLC will do this for you and control the speed of a watt of a DC motor. All the speed drives on the line over there are pulse width modulation. So what we're doing with this is now we can control the DC motor digitally. So DC motors are out there a lot too, because we can control this without directly out of a PLC, right? A real small motor without going through an electronic device. There's no PLCs that controls the frequency. So on AC motors, you'll always have a variable speed drive out there, right? If you're going to control the speed, if you want to control the speed. If you don't want to control the speed, you just put it across Alabama Power and let it run at whatever speed it's designed to run it, depending on the number of poles in the motor. So we'll run a lot into PFETs. We'll run into a lot of the insulated gauges, but we'll run into a lot of those variable speed drives and also pulse width modulation circuits. And then we have what we call integrated circuits. What an integrated circuit is, guys, and this is why electronics are almost impossible to repair anymore. I've got some amplifiers for my stereo at home that everything is individual components, which means if it breaks, I could do what? I could fix it. Just like our trainers. So our trainers use a lot of individual components, so we can fix those things if they break. What they're doing now is they take an entire circuit and they'll integrate it on one piece of silicon. And this is what we call integrated circuit. Now you don't fix that thing anymore. I can't go in and replace a transistor inside an integrated circuit. So what we do now is we understand what it does, and if it don't do what it's supposed to do, then we replace the whole unit. And now the state of integration has got so much that we don't even replace integrated circuits anymore. Hardly any. We do what? Yeah, because they use all this surface mount stuff. And used to, if you looked at a computer, you'd have all these boards and stuff and everything. Even the central processing unit was split up. You know, it was really, when I first started working on computers, the actual central processing unit was a 3-board unit. And then they went to microprocessors, and now the whole processor's in what? One integrated package. So used to you could fix the CPU if you had a problem. Now you can't do that. We still have desktop computers that still use a lot of integration, but they split it up into sections. So those things are still fairly easier to troubleshoot. But these guys right here, if they go out and you do just like if your cell phone crashes on you, you do yeah, and you take them in to fix them. What do? They throw them in a garbage can somewhere, because even technicians don't fix it. About the only thing they do to fix them now is in a lot of your phones now, the batteries even integrated. You know, when the hand phones first came out, the batteries was replaceable. Some of them still do that, which is nice, because now, Apples you don't, they're integrated. A lot of your notebook computers now, this guy here's got a replaceable battery on it. So I could buy 2 batteries and do what? Keep one charged, right? And I did that when I went to Germany. I had 2 batteries, and if it went out, I could do what? I could replace it. Now, even in your laptops, your batteries are usually what? Integrated inside. So it's really, really good. Hard drives, disk drives, they're going to solid state disk drives, which are not as fast, but so just about now, a whole computer, except for the chassis and the keyboard, is usually all just integrated circuits. And usually now it's going to be, so used to you could take away a car radio and you could look into it and you can see all these different components. Now odds are you look into a car radio, you're going to see one big old guy with a big heat sink on it. That's everything. It's the preamp and the amp, power amp and everything in one chip. And the case is big enough so it fits in your dash, right? You understand? It's not going to be long before they integrate that into the dang. In fact, my wife says, no. Yeah, it is. So she's got the touch screen. She does what with her radio? Yeah, the phone, but not that. You change your channel. You don't even have a dial anymore. It uses a touch. So we move more and more to integration, which means we're moving away from component level troubleshooting into system level. Power supplies. This is basic makeup of power supply. We have 2 types of power supply. We have what we call a linear power supply. We're not going to look at the components. We just look like they do. So normally we start off with the transformer. What does the transformer do for? Yeah, of course we know this. And then basically you use the transformer depending on the demands of your load. Then we run through a rectifier. These are going to be your diodes. These are going to convert your AC into these carbons right here. And then we run it through a filter, which converts it into these carbons right here. Now it's DC, but it's DC that's what we call unregulated. And then we run it through a regulator, which causes it to not change its output even though you change load. And then we have what we call a switching power supply, which basically uses PWM. What do they call what's PWM? Pulse width modulation. So what it does is, to get regulation, guys, we have to have feedback. This actually shows the feedback. So we bring it in, we rectify it, and this guy right here is a switch. It changes the pulse width modulation, changes the amount of power that goes through the transformer. Then we re-rectify it, and then we come back, have a feedback that controls the pulse width, the basic control type. These guys, the amount of energy we couple through a transformer depends on frequency, right? The watt, the strength of the magnetic field, the number of loops, and the speed of the motion. So what that means is if we can get away from 60 cycles, if we can get up to 50 kilohertz, then that means my transformers now can be little tiny things. So if you ever looked at a switch mode power supply, you'd see how small they are. Because why? Because now the transformers are hardly nothing because they get a lot of energy through the rate of the frequency, right? You understand that? Plus your filters are a lot smaller. If I took a linear power supply, these filters are going to be huge. In a switching power supply, they're really small. So the advantage of a switching power supply is, number one, is they're going to be a lot smaller. Another thing is that pulse width modulation can take a big voltage and then use a smaller pulse and get the same average out that a small voltage at a little pulse will. So this guy right here can operate off 100. I can plug this into anything between 100 volts and 240 volts and it will still give me the same output. So that means a pulse width modulation or switch mode power supplies have the ability to operate over a wider range. The problem with switch mode power supplies is they're basically unrepairable. So that means when this guy right here does out, we do what? We throw it away and get another one, right? Unless the wire breaks. Linear power supplies, you can fix those. Luckily, our trainers have linear power supplies, so we can fix them when they break. Can't do a switch mode power supply. But these guys are really, really efficient. But they're not repairable, and they're harder to design too. Look at the little bricks you charge your phone. We call them bricks, right, or keys. Little blocks, switch mode power supplies. Very, very small. They go bad, they're sealed up. They usually seal them up to make them more rugged. So if I was to try to tear this thing apart, it would probably be in a chunk of epoxy, right? I screwed up when I went over to Germany. This didn't bother it. All I had to do was buy all I had to have was an adapter here to adapt it over to the German plugs. But my electric toothbrush, it didn't have that feature. So I bought a adapter that plugs it, that you plug it into. You switch it between 240. You could switch it to 240, and it had a transformer in it where it would give you the right voltage. And I plugged it in, and the switch got knocked, and it switched it over to 240. It came through and burned my little charger up. And I got it home, and I said, well, I'm going to see if I can take it apart and fix it. So I broke it apart, and I got into a big chunk of epoxy. It was just solid epoxy. I couldn't get into it. And then I started looking at Walmart, and they sold it for like $11, and I felt like a fool anyway, because I'd spent all this time trying to fix it. And I bought me a new one for $11. So my electric toothbrush is back in play. This is the basic makeup of a control system, guys. So this is the control system. Very important to understand. So what do we have over here on the left? This is where we input information into the controller. Then we have the controller itself, which is either going to be relay logic. Take a motor controls. If you're in the ILT program, motor controls is required. I think in the AUT program, it's one of your electives. This is where you learn something called relay logic. Nothing but relays. Really good course. Could be a what? Could be a PLC. Could be a PID controller. Proportional, interval, differential controller. Calculus. Could be a computer itself. Actually, a computer is a PLC is, but understand a PLC is specifically designed to run machines. This guy right here is not. Right? You understand? It's designed to run games. It's designed to do a lot of neat stuff, but it's not designed to run machines. Could I run machines off of it? Sure, with the right interface, I could. I could back. They used to have a parallel port on the machine, which got lost, but we literally could run stuff off that thing by programming. But sooner or later, we're going to have to develop a what? An output. So this computer is a control device. So we got what on it? We got inputs. Then we got the controller inside, right? You understand, it's processing the information from the input. And eventually it's going to have to do what? If any one of these are gone, then basically you don't have a control system. So what happens on your cell phone when you break up that touch screen? It don't work anymore. You got, what happens on this computer if the keyboard stops working? Right? You understand that? So we got to have this. We got to have all these devices to make up a control system. And they got to intermarry together. So we're going to deal with switches, we're going to deal with relay contacts, and these things called systems. Here we're going to look at a little bit of relay logic. We do have relays on all of our devices. But not on both lines, we have relays. And then we have program control. PID, we're not going to look at that for the semester. We might talk a little bit about it. Definitely got computers. Microcontrollers, we'll show you all microcontrollers. A microcontroller, a PLC, is a very expensive thing, right? You understand? The biggest advantage of a PLC, of course, is that it's set up to be programmed by languages that people understand. But we have different trades or different disciplines that come up through different trades that needs to learn how to program a PLC. So originally when PLCs came out, they programmed in what we call ladder logic, because what they were doing is they were adopting electricians over to computers. So they made them program in a logic language that electricians understood. They understood relay logic. So it's very, very similar to that. But then we have people that comes up through programming computers. They program in text language. Right? Very complicated. Well, it's complicated for people trying to learn it, but once you learn it, then that's going to be your preferred method to program it, right? So another language that they've added to PLC is called structured text language, which is basically a text language. You've got to learn a lot of commands and you've got to learn a lot of syntax. Your microcontrollers, that's all they program. Your microcontrollers, they're computers, but usually when you program those and you put them out there, they serve one task once they've done that. We can buy, we'll show though, the little Arduino microcontroller we have costs $30. You can buy it on Gamaco for $30. But it's just a piece of plastic until you learn how to do what? Right. Till you learn how to connect inputs to it, till you learn how to connect outputs to it, and also how to program it. And it programs in a structured it programs in the text language. And I'll show y'all some of that. And I'll show y'all that control. So you might run into those. Do you need to know how to program them? Well, you might, but that's something you'll have to get. We're not going to teach that right here. But you need to learn what they do and how to identify when they're what. When they're bad or they got a malfunction. It always is strange to me. You've got a PLC that's been running in a system for a year, and they start having a problem in it, and you start having people break into the programs and try to fix it with programming. There's probably a 99% chance it's not the programs, it's what? It's either you're having a problem with your what? Your inputs or your outputs, which is probably 90%. So guys, let's take another 2-minute break. Push buttons. It's getting more and more. We still have to have push buttons because they're mechanical. We don't like to totally turn things over to software. So we have these, we call them HMI panels, which are human machine interfaces. And most of these use touchscreens. So you simulate push buttons, you simulate all kinds of stuff, switches and stuff like that, but they're all software.
Question. So we got a panel that works, but it's not touchscreen, but you still can see the screen. You got to push buttons.
All it is just a monitor. Imagine like this computer right here.
So we would consider a HMI panel?
Probably not. It would be considered a display. Just like this is not HMI. Well, that's not true. This one is the touchscreen. So for it to be an HMI panel, you have to be able to use it directly, as far as I know. But the touch panel would be technically a push button is an HMI device. Human machine interface. So anything, so the panel itself, but the combination of the two. So any switch is an HMI. But it's just like every operating system. Is what we call a disk operating system. But when they first came out with the first operating system, it was a disk operating system. They called it DOS. So after that, they didn't name anything after that DOS. They call them Windows 95, and all. Even though technically every one of them is a disk operating system, and that's the same thing true. So we have devices called limit switches. Limit switches have been around for years. Technically, it's a proximity switch, which means it looks for things to be at a certain spot. But we don't call it a proximity switch. We call it a limit switch. And that's the same technical. So we don't call push buttons an HMI device, even though it is. Technically, it is HMI, right? You understand, the human machine interface. We usually call HMI devices like touch screens and stuff like that, or even, that makes sense? So, technically, we have a lot of things that could fall under the category of HMI. So push buttons could be HMI. but we don't call them HMI. We call them push buttons or switches. We don't use very many switches we do, but we don't call them switches like light switches. You won't see toggle switches. They're toggle switches.
So the one on the far right here?
No, it's not even in there. Toggle switch would be, no, this is not a toggle switch. We call this a selector switch.
Okay.
It don't toggle.
Okay.
So usually toggle switches have one operator comes out. So a light switch is what we would call a toggle switch.
So that looks like the one over here.
Yeah, but what we're trying to do, what you got to understand is that any switch that we use in industry has got to be able to be operated with people wearing gloves. Got to be. So the problem we have with these little old switches is they get really hard to operate with a glove. So this is why we don't use toggle switches in industry. We use what we call a selector switch. These are going to have a big knob sticking up that you can do what? You're not flipping it up. And another thing, toggle switches are notorious about accidentally being turned on and turned off. So this is why light switches are supposed to be mounted, except for 3- and 4-way switches, with the on pointing up. So if you actually hit into them, you'll turn them off, right? You understand? You ever notice that? So the on is on, you only see the on when it's up, you see the off when it's down. So toggle switches they're notoriously about accidentally being turned on or turned off. Just by accidentally doing what? Touching. So this is why on the launch controls for these stuff, they'll have like we had toggle switches on our airplane, but they had an operator on there that they had to literally do what? Raise the cap on to flip the thing on the airplane. So you got to be real, because without that, the flight engineer might actually scratch his head and flip the switch off and turn the gas off going to the plane, right? You understand? So toggle switches are bad like that. Selector switches, these guys, they're usually indented, which means you put them in one position until what? You put them in another, and they stay in that same position. And they can be operated with a glove, so they're a lot safer. And it's hard to accidentally turn something than it is to make it. And this is why just about all your switches, your actually push buttons, are inside something. Can y'all see this right here? So notice the push button itself is flush with an outside unit that comes around it, right? You understand? So you literally got to do what? Push it down. Except for e-stop buttons. E-stop buttons have got to be very, very easy to hit. You should be able to hit them like this, right? Instead of thinking about doing that, you can just hit them. So e-stop buttons, emergency stop buttons, they're supposed to have a mushroom head on them. So we call them mushroom, right? And either, depends on how they work. If they are the main means of e-stop, they're supposed to latch down in the e-stop position. And then you literally got to do what? Pull them out, but a lot of them, depends on where you're at, you literally got to push them in and turn them and then pull them out. So it all depends. Our e-stop buttons operate a relay. So these e-stops over here, you can pull them out without doing what? Twisting them. All the robots over there, the e-stops on the robot, you literally got to do what? Push them in a little bit, turn them in a direction, and then they'll come. The Festo line has no e-stops. It all depends on where you're at and what they require. The e-stops we have on our manufacturing line, the ones on the old boards, the white boards, those latch down. The one on the new boards, they latch down too. Yeah. So it all depends, it all depends. That's a good question. Are we okay? Switches. These are digital devices, which means they're either what? Yeah, on or off. Or in a different position. We do have where they're on in both directions. It's just they control a different circuit, right? And we'll look at that in a minute. Then we have our sensors. We could think, what we can do is, what does a sensor do? What does these sensors do? What do our senses do?
Determine where things are,
Well, how do they do that?
power,
They take a physical quantity and convert them over to an electrical quantity so our brain can process it. So your brain processes electricity. It does not know touch. It does not know smell. It does not know anything. It does not know equilibrium. It does not know pressure. It does not know anything, right? You understand? So first of all, we have to get that thing, we have to get that quantity, that temperature. So I can sense temperature, even though that's not listed as one of our 5 senses, but we can sense temperature, right? But my brain don't know temperature. What does it do? We have sensors out there that takes temperature and converts it over to an electrical equivalent, and then that travels up our spinal cord to our brain and goes to a special portion of our brain that processes what? Temperature, right? Our brain can't see, but we have eyes, right, that takes light and converts it over to electrical signals proportional to the amount of light that it sees in that color, right? So we have these rods and cones in the back, right? Cones are what? Cones are red, white, and blue, and rods are shades of gray, I think. Yeah, so we got one set that sees nothing but black and white. It sees shades of gray. And then we process all that, and our brain sees color, which is really, really neat. So a sensor, an electrical sensor, does exactly that. It's got some type of sensing element in there that takes some type of physical quantity and converts it over to electrical equivalent so we can process it with electrically. So now we can process it with electrical or electronic devices. So we can sense presence if something's at a certain spot, right? You understand? Distance, position, pressure, flow, light, sound, temperature, speed, weight, color. There's all type of sensors. So just about anything we can sense, by George, they can develop an electrical sensor that can do what? They can sense that. So this is not all of them. We can sense all kind of things that's out there. These are just the ones we look at that we don't even sense weight over here. So what we have over here, we have length on our lines. We have presence, we have distance, we have position, we have pressure. We don't have flow. We have light, and we don't have. We don't have temperature, but we have speed.
not weight.
We don't have weight. We don't have anything over there that senses weight, but a company might do that. So I worked at they sensed weight really, really neat. Dog food plant in down to Go Kiss, the Go Kiss plant. We had some electronic scale, computerized scales that I worked on there. Yeah, no, not in Bessemer. The ones over the First Avenue Viaduct. You used to have the big dog sign up there with a wagging tail. I think that's gone. Over there by Slosh Furnace, the dog food plant. In fact, that's where they used to go and eat, up under the overpass over there. That's where their tables were. They went and eat. You talk about something that's gross, guys. Dog food plant. Oh, you can smell this one over here. Yeah. But we had a lot of computerized scales out there. It's very important. And they would fill the dog food up, and they would run. This is literally how they did it. The sense weight is they would run it through a big old vat of water that had a certain specific gravity to it. If it sunk, it was the right weight. If it floated, and they called them floaters. Kind of like they call people that drown, right? They called them floaters. And they would give you every time I'd go over there, they would want to give me a case of dog food, but it was their floaters. Because once it's sealed in the can, they couldn't really do anything about it. So their people haul those away. But that was a method of sensing what? Weight, but it wasn't taking it and getting it electronically. So I worked for a year of a company that's what it was scales. And scales then were computerized. It's really, really neat. So I got a present. We had a problem with our scales up there. They call it the chicken feet scales. It's where they made their chicken dog food, and basically they'd bring these big old barrels of nothing but chicken feet from these processes. And they take those big barrels, and they knew how much their barrels weighed, and they'd put it on the scale so they could tell how many chicken feet they had, because that's the way they'd pay for it. And their scale stopped working, and we was over there looking at it, and I got under and looked in the waste bridge, and the floor was moving. And I said, and they said they came over there and brought a set of forklifts up and lift the weighbridge up and moved it, and it was nothing but maggots. The whole floor under the weighbridge was maggots. And it didn't even bother them. They went out and got a spray, and they sprayed it on the thing, and it killed all of it instantly, and they swept them up. We put the weighbridge back down. And but they had so much pressure on it from the maggots, it was the scales wasn't weighing. Yeah, and I told that guy, he was the boss, and I says, man, he says, how do you eat lunch out here? He says, I've been working here for 15 years, Rich, and I've never ate lunch while I've worked here.
He never ate lunch.
That's what he said. I said, I believe it. I didn't see rats. Now, I saw some rats out of U.S. Steel. I saw some rats out there. Yeah. Them suckers, when you walk on them, they don't run. So, sensors fall into two categories, guys. We got analog sensors and we got digital sensors. Y'all understand the difference? So what's the difference between analog and digital? Digital either on or off. It has the ability to fluctuate, right? So temperature sensors, if I'm looking for it to, like my temperature sensor on my house, that would be digital, right? Because I either turn my thing on or off. It doesn't, but it's got a display on top of it that tells me the actual temperature. Well, that would be what? That would be analog, right? That can move. Yeah, it changes the temperature. So temperature is analog value, right? So if I'm trying to process so the sensor on your oven, that's probably an analog sensor, right? You understand? Because what can you do? You can set any temperature you want. And we'll talk, but we have to run it through some type. So analog sensors, most of your sensors are analog. To convert it to a digital sensor, we run it through something called an analog to digital converter. So just about all your sensors that we're going to look at, the actual sensing element develops an analog output. So we have to add something, except limit switches. Limit switches are digital. Then we got two categories. We got contact and non-contact sensors. What do you think that means? Contact means it's got to make physical contact with what it intends to measure. Right? It would have to be a contact sensor.
That's kind of like the sensor over the line. It detects that a block is there.
Yeah, but it don't have to have contact with it. So that would be a non-contact sensor. So a contact sensor has to make physical contact with what it's going to measure. So some temperatures are contact sensors.
So then would a light sensor be considered contact?
Well, no, that's not the sensor. That's the light. The sensor itself is not making physical contact. The sensing element has to make physical contact with what it's going to measure. So a thermometer, you have to stick it in your mouth, right? You understand? So what would be a what? Contact sensor. You go to the hospital, I've seen them before, now they point a light at your head and they can get your temperature without even doing what? That would be a non-contact sensor. So is a temperature sensor contact or non-contact? Well, it all depends, right? Light sensors were definitely, ones that use light is definitely non-contact because the sensor is not making physical contact with what it's measuring. So a limit switch will always be a contact sensor. A limit switch is a mechanical switch. Let's see if I got limit switches. So these are limit switches. So they're either rotary or they're push. And we got what we call an operator. So this guy right here, when something hits it, it moves that operator around, causes it to turn, causes a contact to either close or open. But that operator's got to make physical contact with what it measures, right? You understand? So all limit switches are contact sensors. Then we have, this is where we get, so a proximity sensor is when it tells when something is at a certain spot. If it's not at the spot, it would be false. If it is on the spot, it would be true, or how it's set up. A limit switch is a proximity sensor. But it is not called a proximity sensor. It is called a limit switch. So what has happened is the term proximity is turned out to be sensors that do not make physical contact. So that's the way it stands for now, right? You understand? So proximity sensors are sensing when something's at a spot, not a range of spots, right? But at a spot, but it does not make physical contact with what it's trying to measure. The sensing element. So we're going to have some photoelectric sensors we'll look at. Through beam, optical interrupters, diffuse, and retroreflectors. So we need to understand those. We don't need to understand how they work. We just need to understand what they do, right? How do they sense? How do they sense with light? Then we have what we call inductive sensors. These are non-contact sensors. These guys sense metals. That's the only thing they sense is metals. Then we have capacitive sensors. These guys can sense about anything. How they do it? I don't know. I do. But you don't really need to know that, right? So if I needed to sense glass, I could use an inductive sensor. If I wanted to sense glass, I couldn't use an inductive sensor. But I could use what? I could use a capacitive sensor. I couldn't use a photoelectric sensor because the light would pass through the glass. We're going to look at a reed switch. A reed switch detects the presence or absence of a magnetic field. But it does it electromechanically. Then we have a Hall effect sensor. A Hall effect sensor senses the strength of a magnetic field, but it's going to do it electronically. How does it do it? I don't care. Right? You understand? In this class, in sensors, we'll talk about that. We got ultrasonics. We can use ultrasonics for a lot of different things. Normally we use this to sense distance. We could also use it for speed. We could also use it for presence. Then we got our other contact sensors. These are what we call force sensors. This is force and pressure. We do have some of those on our line over there. Flow. What is a flow sensor doing? How fast the fluid is flowing, right? And what's a fluid? Huh? Anything that doesn't have a fixed shape. It can move easily, right? You understand? And takes the shape of whatever you put it in. So fluids are gases or liquids. For years I thought fluids were liquids. Before you take the class, yeah. So fluids, people think is water, but air is fluid, right? Because it don't have a fixed shape, right? You understand? It can move easily, right? Flows, it can float, right? It takes the shape of whatever you put it in. So it's either a gas or a liquid. So if we're going to move fluids, sometimes we need to sense how fast it's flowing. Speed. Speed deals with usually mechanical devices. So flow would be speed, but that would be how fast fluids are moving, right? You understand? Flow rate. Speed, we're usually talking about mechanical devices. We'll look at tach generators, we'll look at incremental encoders, and we'll talk about variable. Not how they do it, but what they do, right? You understand? Temperatures, we're going to look at thermistors and thermocouples. Position sensors. So what's the difference between proximity and position? What's the difference between position and proximity? Probably what a proximity does, it can, things can be in motion, but a proximity sensor says when it's at a spot, right? So proximity be now where y'all at. Y'all are at a certain spot. So proximity sensor, I would only be able to detect you if you was there, right, Morris? If you was over here, I couldn't see you, right? That makes sense? So proximity sensors are when it's at a certain what? Spot. Position sensors would mean you could be anywhere in here and I could find you over a set range. Now I couldn't see you out that door. I couldn't tell where you sat out that door because now you're out of my what? My range. So all position sensors have a limited range. But as long as it's in that within that range, then the proximity sensor is going to be able to find it. So it says I'm here, right? So we look at potentiometers. Potentiometers is, we have several potentiometers back here. We have 2 on the Amatrol line, and we have 1 on the Festo line. It's used to detect position, right? You understand? Then we have what we call a linear voltage differential transformer. We'll look at that. We use a lot of encoders. But encoders are big. Computers love what? In fact, computers only understand digital, right? You understand ones and zeros. So if I'm going to bring an analog sensor into a computer, then we're going to have to run through something called an A to D converter, analog to digital converter. If I'm going to control a linear device with a computer, then I'm going to have to run through a what? A digital analog converter. D to A's and A to D. So we're okay. Everybody okay? So we're just about ready to get. So digital sensors, analog sensors, are we okay? So temperature would vary in what? Analog. Pressure varies in analog. Light varies in analog. Just about everything in nature is analog, right? So we're analog. So all our sensors are analog. So not only can I sense if I'm touching something, I can sense how hard I'm touching it, right? You understand? I can sense when I get off of balance. I can figure out what to do to correct myself, right? I can sense temperature. I know when it's hot. I know when it's cold. I know when it's nice. I know when it's not nice, right? You understand that? So we are analog. We are analog. Our eyes are analog, except when we do this. That would be what? That would be digital. So I guess we do have some digital. We know when we inch and we know when to scratch, right? But analog cannot be processed by a computer, even though we know that it has to be, right? Because we're dealing with computers that are designed to run machines, and they're operating in an analog world. So if I need to measure analogs, then our computers are going to have a what? Some type of analog to digital converter. It's becoming so popular now, guys, that just about all your PLCs that come out now have A to D capabilities inside the PLC. I forgot how many the 314 has. So the Amatrol line is running Siemens S7 314 PLCs, and they have several analog inputs, outputs.